All right. Hello, everyone. Good afternoon. This is Fahim from Florida State University. I'm a third year PhD at working at Computer Architecture and Systems Research Lab. We are a group of 8 graduate students led by our professor, Dr. Wei Kuan Yu. And we have been working on different collaborative projects with the data analysis group led by Catherine Maurer at Lawrence Livermore National Laboratory. So this project was one of the very first exploration projects that I overtook and as a PhD student. And last year we published our work in the International Conference on Parallel Processing, or ICPP 2019. And this research paper was titled as I/O Characterization and Performance Evaluation of BeeGFS for Deep Learning. So without further ado, okay. I'll start. So these are the list of our authors. Some of them are from the Florida State University and some are from Lawrence Livermore National Laboratory. And I thank all of them to give me the opportunity to talk on behalf of them on the project. And this is the quick outline of our today's talk. Firstly, I'll talk about the motivations and the key contributions of the project in the overview section. Then I'll try to briefly introduce you to the BeeGFS architecture as we explored, and I think most of the people here knows much better about it, so it will be a very brief section. Then I'll talk about the deep learning frameworks and the I/O patterns we have explored, and also the benchmarks we have used for the experimental, for generating the experimental results. And then in the next section, we'll talk about the results and the key observations, and finally the conclusion and the future works. So firstly about the overview. So we all know that we are very interested in deep learning applications because not only it is used on top of HPC infrastructure, but also as a HPC community, we are very interested in it. Apart from that, we know that deep learning applications are everywhere, from image processing to even autopilot driving systems. So deep learning applications made us very interested. And also, on the other hand, we are also interested in BeeGFS because at that time it was a very well-known and very emerging parallel file system. So we wanted to have an evaluation out of our interest. And another point to be noted here is, in case of using deep learning applications on HPC systems, we keep in most of the cases, we keep the data set on the parallel file systems like cluster, GPFS, or in our case, BeeGFS. So taking all these motivations into account, we performed our research on evaluating BeeGFS, focusing solely on deep learning application workloads on HPC systems. In our project, the key contributions were we identified the I/O patterns posed by deep learning applications by using I/O profiling tool like Darshan. And we also evaluated the impact of read and write on BeeGFS using conventional benchmarking tools like IOR and MD-test. Then we used MD-test for analyzing the metadata performance on BeeGFS. And finally, we evaluated BeeGFS using deep learning application benchmarks with real application benchmarks. Now, about the BeeGFS introduction, just like any other parallel file system, it has a management server, and it can have only one management server, which keeps track of the initial connectivity information among all the services. Then it can have a metadata server that can be associated with one metadata target per server, and it maintains exclusive part of namespace for each metadata service. And it can have object storage servers, just like any other parallel file system. We can have one or multiple object storage targets. Each object storage target can be generally a rate set with POSIX compliant file system. And finally, the file system client for exposing us to the APIs and configurations, changing configuration in the BeeGFS setup. We have this file system client kernel module. Apart from that, there is another one, Admon. service. And I tried a little bit on that, but I have skipped it here because it's out of context for our research project. So now about the deep learning IO pattern section. So for the deep learning frameworks, we have used two basic deep learning frameworks. Firstly, as we are a collaborator with Lawrence Livermore National Laboratory, we have used the Livermore Big Artificial Neural Network Toolkit, or LBANN, that is solely developed in LLNL. This is a neural network toolkit especially designed for HPC. And for the context of our project, the important information here is in case of LBANN, we have dataset specific specialized input pipeline. For example, we have, let's say in the LBANN code base, we have a class that handles the ImageNet dataset and so on. And we also started, after analyzing with LBANN, we started using TensorFlow and Horovod. We all already know that TensorFlow is a machine learning development platform that is very well known and very frequently used by the community. That is developed by Google. And apart from that, Horovod that helps enable HPC features like enabling MPI for having distributed TensorFlow on distributed version of the framework like TensorFlow and Torch, etc. So in case of TensorFlow, sorry, I think the slides are running automatically. I'm sorry about that. So the TensorFlow provides dataset APIs for importing data while in the training phase. So in our case, we have used the default dataset API features for developing an initial prototype ImageNet reader pipeline using TensorFlow and Horovod. So this was about the deep learning frameworks we have used. And about the deep learning applications and datasets, we have used LXNet and ResNet50. LXNet is a 8-layer convolutional neural network for image recognition. And in case of using LXNet, we have used ImageNet dataset. And we kept the ImageNet dataset on the BeeGFS instance we have in our Livermore's Catalyst cluster. And about ResNet50, we already know this is a 50-layer deep residual network, and this is also used for image classification. And both LXNet and ResNet50, these two applications were run on top of LBANN. And when I already mentioned about using TensorFlow and Horovod, we have developed a ImageNet data reader pipeline on top of it and used it as a another benchmark or prototype application benchmark for evaluating BeeGFS for deep learning applications. And a little bit brief introduction about the ImageNet dataset. ImageNet is a very well-known image dataset that we use for training the deep neural networks that deal with image processing and image recognition and classification. So this is a huge labeled image dataset that has around 1.2 million images. And according to our experiment, the average file size of the ImageNet dataset is about 100 kilobytes. So firstly, we were curious about knowing what is the exact IO pattern and what is the main challenges that are posed by the deep learning IO, deep learning applications while in the training phase regarding the IO workload. So here in these two pictures, we can see like in the left picture, the x-axis shows the POSIX access sizes and the y-axis shows the count in total for each size. And in the left picture, we are showing the Darshan output for the POSIX exercises and the count when we ran ImageNet Reader on LBANN. And in the right picture, we are showing the TensorFlow dataset API's input pipelines output that was reported by LBANN. So as we have seen that very small IO accesses are posed by access requests are posed by both LBANN and TensorFlow, reported by the Darshan 3.1.7 profiling tool that we have used. So the main challenges here are, though we are reading very small amount of data, we have to go through metadata overhead every time, because as I mentioned, ImageNet itself has very large amount of files, and because of this many number of accessing this many number of small files, we are reading less amount of data, but we have to go through huge amount of metadata overhead. And another thing is, in the beginning of each epoch in deep learning application training, we have to do a global randomization so that we do not get caught into local optima, or the deep learning application does not learn the ordering of the images. So we have to do full randomization. And because of this randomization, we cannot take advantage of the inbuilt caching in parallel file systems or any traditional parallel file system. So the basic challenges here are, we are reading very small amount of data for each file, but we have to access each file. So we have to go through the huge metadata overhead that has to, I mean, that is introduced by the parallel file systems on HPC. And apart from that, we cannot use the caching mechanism that is used for, or maybe some file, or maybe some IO aggregation policies that are already built in different parallel file systems. We cannot use that because we have to deal with the randomization in the beginning of each epoch. So as we have been introduced about the basic challenges in the deep learning IO, in the IO workload of deep learning applications. Now let's move on to the experimental results and the key observations section. So in our experiments, we have used this mentioned system configuration. All our experiments were performed on the Catalyst cluster, that is an in-house cluster in Lawrence Livermore National Laboratory. And my co-author Todd here was responsible for all the administrative and system administrations for the setup and installation, and also maintenance of this instance of BeeGFS setup. And in our case, the BeeGFS size was 338 terabytes, and we used BeeGFS-7.1.2 for our evaluation. And in the setup, we had 12 server hosts with QLogic Infiniband QDR interconnect. And we had 12 object storage services, each attached with 2 object storage targets. Each object storage target in our case was 4 hard disk drive with ZFS RAID Z and ZFS intent log on SSD. And apart from that, we used level 2 adjustable replacement cache on DRAM. And for the metadata services, we had 36 metadata services on 12 server hosts. And each metadata services had exactly 1 metadata targets. And we had 3 metadata services per server host running on the setup. And in our case, each metadata target was 4 SSDs with ZFS RAID Z formatting, just like the OST, but in this case, we didn't have ZIL enabled. So for the benchmarking tools, we have used Interleaved-Or-Random, or IOR. That is a very well-known IO benchmarking tool. And we have used 2.10.3 version of IOR. And for doing generic IO tests on the parallel file system instance setup we generated file per process and single shared file read-write workload with 240 gigabytes total file size in both the cases. And for the metadata tests, we used MD test 1.9.3 benchmark, and we have generated the workloads of file create, file stat, and read operations. And in case of MD test, the read operation is actually opening a file, then reading 1 byte from it, and then closing a file. So it's also essentially a metadata workload that exposes the users to the file open and close. And for the workload, we had 3 types of hierarchical directory structures. Firstly, we tried with shared file directory structure, where we had only 1 file in a single directory. Then we had flat directory structure, where we had 0.4 million files on a single directory. And apart from that, we also had a single depth hierarchical directory structure to replicate what we have in the ImageNet dataset directory structure. In this case, we had a single depth hierarchical directory. This is like segregating all the 0.4 million files into different subdirectories inside one parent directory. So we'll go into more detail when we discuss about the results in the next few slides. Apart from that, for the deep learning benchmarks, as I've already mentioned, I'm reiterating again, we have used LXNet and ResNet 50 on ImageNet on the LBANN framework. And apart from that, we also had an ImageNet reader pipeline on top of TensorFlow Dataset API and Horvath. So firstly, we started up with a very microscopic analysis of the I/O performance. So for that, we started up with a single client read performance test. In this case, for these pictures, the left picture shows the file per process read performance, and the right picture shows the single shared file read performance. And in the x-axis, we have increasing number of processes per client. In this case, we have only 1 client for these pictures. And in the y-axis, we have the bandwidth. And it is the same for the right picture as well. So we have found out from our results, another more thing is like we have tested it for different stripe counts. And in our case, the stripe size was 512 kilobytes. So from these results, we have found that NN, or file per process read bandwidth, reaches a saturation point. And this is due to the network bandwidth, because we are using only 1 client in this case. And for N1 read bandwidth, according to our exploration, it was behaved a bit differently, because for lower stripe counts, we found that the read bandwidth was decreasing a little bit, but for higher stripe count, like stripe count greater than or equal to 4, we had similar results for single shared file as we have got for the file per process workload. So afterwards, we also tried testing the write performance that is posed by the IOR benchmark. And for the write performance as well, we got that NN write bandwidth scales up very well with increasing number of processes per node. And the single shared file workload did not scale that much, or we did not found it scaling that as good as NN write workload. And then we started doing the scale out write performance and the read performance. So in this case, in the y-axis, instead of varying the number of processes, we varied the number of clients, and we kept the number of processes as equal to 8, because that was one of the number of processes that we got saturating in the last single node experiments. And we also varied it for different stripe counts for stripe size 512 kilobytes. And we have found that the NN read bandwidth scaled very smoothly with increasing number of clients. And also it was good for N1 read bandwidth as well, but it was not as good as NN read bandwidth. So for the write performance, it was also showing similar trends. NN write bandwidth shows good scalability, as we can see, and N1 write bandwidth is almost as half as the NN write bandwidth. So afterwards, we were thinking about, okay, in this case, the transfer size was 1 megabytes. Why don't we vary the transfer size while keeping the number of clients to 16 and the number of processes per client to 8 processes? And in this case, we wanted to duplicate as much as we can using IOR, the read access or read access pattern actually for deep learning IO workloads. So we wanted to see if the transfer size is very low, what happens there. So we found that when we change the transfer size, NN workload handle the changing transfer sizes very well. When we increase the number of, when we increase the value of this transfer size from 16 to 2014 kilobytes, KB bytes, we found that the NN read bandwidth and also the NN write bandwidth increased and scaled well. But for N1 write bandwidth, it was not that good as NN write bandwidth, as we have mentioned. It actually reproduces the results we have experimented before. So another thing here is N1 read bandwidth is not that important for deep learning training IO, because deep learning training IO is kind of like an M workload. Like in most of the cases, each process is responsible for reading multiple files per process. So we were thinking about what happened when the transfer size is about 128 KB bytes for NN workloads. So it was around 8,000 maybe bytes per second, or 8 gigabytes per second read bandwidth. So by analyzing all these results, we have reported these key observations, as it is very apparent that NN workload is almost always better than N1 workload. So another thing, as I have already mentioned, NN workload is not exactly what DL training IO would pose, but it is a bit closer to that. Closer with respect to N1 workload. And another recommendation is like when we are doing regular checkpointing and logging in deep learning applications or any other application that do this on top of parallel file systems like BeeGFS, we should avoid N1 writes. Instead, we should use NN writes. And in most of the cases, I have seen that only one rank is used for that, and only one rank writes on the log files and checkpointing files. And another thing to be noted is increasing stripe count is not always necessary. So in our tests, we have seen that if the stripe count is greater than or equal to 4, it's almost scales well. I mean, it's most of the time it's okay from the performance perspective. So if we want to balance the resource utilization and the performance, we can think about using lesser stripe count, and because lower striping leaves more devices available with reasonable performance. So later we found out very interesting results on the metadata performance. As I have mentioned already, we have used 3 types of directory structures: flat directory structure, hierarchical directory structure, and shared file directory structure. And in these three pictures, in the leftmost picture, we have results for the file stat. In the middle picture, we have results for file read, or as I mentioned, it's like opening a file, reading 1 byte, then closing the file. So it is essentially file open and close, metadata workload. And finally, in the right picture, we have the results for file creation. And we found that for file stat, the performance is good for both flat directory structure, while we have all the 400,000 files on a single directory, and also it's good for the hierarchical directory structure, where we have all the files distributed into number of subdirectories, where the number of subdirectories is equal to number of processes we had here. And in case of file open and close or file read metadata posed by MD-test, we have seen that single depth hierarchical directory structure alone wins against all the other directory structure configurations. And for the file creation as well, we had the similar trend for hierarchical single depth hierarchical directory structure. So we have enlisted this key observation in our paper, and we have said that hierarchical file organization is beneficial for metadata management in BeeGFS, and data sets like ImageNet is actually arranged in that way. And we have also recommended that the dataset files, if anybody is creating a dataset, they might consider arranging it in a hierarchical directory structure manner. So now for the deep learning application workload tests, and in this case we had number of processes per client equals to 8, and number of clients equals to we increase the number of clients from 4 to 32, and in the x-axis we have the number of clients, and in the y-axis we have the latency that is broken down into the read time and the metadata time as reported by Darshan. And in the right side of the y-axis, we are also reporting the bandwidth that is shown by the by this line curve. And here we can see in the orange curve, we are reporting the read time, and in the purple curve, we are reporting the metadata time as reported by Darshan. So for LXNet over ImageNet, we saw that the read time decreases with increasing number of nodes. But on the other hand, the metadata time actually did not decrease. Instead, it remained almost the same, and in some of the cases, it increased. So metadata overhead governed the overall throughput in our case. As we have mentioned in the deep learning IO challenges, that we have to go through a substantial amount of metadata overhead. And we have found this trend in our deep learning application workloads training results. And apart from that, we used ResNet 50 over ImageNet on LBANN. And in this case, we've seen similar results for ResNet 50 as we got for LXNet deep learning application. And we also see here that though the read time is lessening, but the metadata overhead is governing the whole IO time. And in both of the cases, the bandwidth remained, bandwidth was okay, because in our varying transfer size results, we got that for 128 kilobytes transfer size, we had around 8 gigabytes per second bandwidth. And apart from that, we had some initial level tests on distributed TensorFlow. I would say this is initial level because this prototype was like when we are working on the research paper, we thought about adding TensorFlow in our evaluation as well, in addition to the LBANN framework. So we had some initial level distributed TensorFlow implementation, prototype implementation for reading the ImageNet data set from the BeeGFS parallel file system instance. So in this case, we found that, as Darshan reported, we found that less data was read compared to LBANN. And because of that, the bandwidth was low. But the same trend for the metadata time we have seen here. Like in case of metadata time, the time did not decrease, or it did not, it could not leverage the increasing number of clients, the resources that are that became available by the clients. So metadata is still a notable bottleneck in this case. So we enlisted the key observations we got from the deep learning application workload. We have seen that BeeGFS can reasonably handle the I/O pattern that is posed by LBANN, and because the read time lessens with more clients, but the metadata overhead increases, but it increases less steeply. And the directory structure of ImageNet is helpful for BeeGFS that we have observed from this MD test, that by replicating the directory structure that is available in ImageNet dataset, and we have seen that single depth directory hierarchical structure in ImageNet might have assist the metadata manager. And TensorFlow. So the thing is, we have used Darshan and we have used Python wrappers on TensorFlow. So there are some more specific details we need to go through in case of our TensorFlow prototype implementation. So according to our observations so far, we have seen that there might be some internal optimizations in the TensorFlow's read file through Python wrapper that invokes very tiny file reads, as we have seen from the very first I/O pattern related results we have shown, and also from the very last TensorFlow's results we have shown. We have seen that the read bandwidth was low because there were very small amount of files read, but a lot of files were accessed, and they have to go through the metadata overhead. So in all the cases, the metadata handling was a very notable bottleneck in case of both LBANN framework and also TensorFlow and Horobot framework benchmarks. So I'm almost in the concluding part. So in conclusion, I'd like to say that we performed in our research paper very microscopic data and metadata I/O performance evaluation on top of BeeGFS parallel file system instance we had set up on the Catalyst cluster. We discussed all the results and observations in the context of deep learning I/O patterns, and those I/O patterns were all posted on BeeGFS parallel file system instance we have. And about the future, as I have mentioned, we had a very initial exploration on the TensorFlow part. So we plan to perform more in-depth analysis on that by using TensorFlow and Horobot, or we might think about using Torch as well. And apart from that, for the BeeGFS feature evaluation, we are also interested in evaluating BeeGFS on demand. That might be useful as a burst buffer file system. That might be an ephemeral instance of burst buffer file system, and that might be useful for different checkpointing in deep learning applications or any other HPC scientific applications. We have a plan to evaluate BOND, and apart from that, we also are interested in a storage pool that might be useful for handling heterogeneous storage stack on HPC cluster. So now I would like to thank the sponsors of our project, Lawrence Livermore National Laboratory, of course, and National Science Foundation. So that's the end of my presentation today.